Our universe is filled with countless mysteries and secrets, from the vast expanses of space, teeming with galaxies, stars, and planets, to the massive forces that control the very fabric of reality. Let us take you on a fascinating journey to some of the most mind-blowing mysteries in deep space. Embarking from the aftermath of the Big Bang, a monumental explosion that occurred approximately 13.8 billion years ago, we venture into an era where the universe was in its infancy, teeming with high temperatures and dense energy. This initial burst set the stage for the universe's formation, marking the beginning of space and time as we understand them. In the fleeting moments following the Big Bang, the universe was an incredibly hot and dense point. Within fractions of a second, it began expanding at an exponential rate, cooling as it did so, allowing for the formation of the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces. As the universe expanded and cooled, conditions became ripe for the creation of the first subatomic particles, such as quarks and electrons. These particles, born out of the energy from the Big Bang, eventually combined to form protons and neutrons. The universe, however, was still too hot for these protons and neutrons to combine into atoms. It wasn't until about 380,000 years after the Big Bang, as the universe continued to cool, that protons and neutrons began to combine to form the nuclei of the simplest elements, hydrogen and helium, through a process known as nucleosynthesis. Hydrogen, the most abundant element in the universe, and helium, the second most abundant, were the primary products of this early nucleosynthesis. Trace amounts of lithium were also produced during this period. The creation of these elements set the foundation for the complex chemistry that would eventually lead to the formation of stars, galaxies, and planets. As the universe continued to expand and cool, gravity began to pull together clouds of hydrogen and helium gas, leading to the formation of the first stars. These first stars played a crucial role in the evolution of the universe. Through nuclear fusion in their cores, they forged heavier elements such as carbon, oxygen, and iron. The life cycles of these stars, including their eventual explosion as supernovae, dispersed these heavier elements into space, seeding the cosmos with the ingredients necessary for the formation of new stars, planets, and eventually life itself. The cosmic microwave background radiation, or CMB, is a faint glow that permeates the universe, offering a snapshot of the cosmos a mere 380,000 years after the Big Bang. This glow is not just a relic of the past, but a treasure trove of insights into the early universe, its composition, and its evolution. The CMB's discovery in the 1960s was a pivotal moment in astrophysics, providing strong evidence for the Big Bang theory. This radiation is the afterglow of the universe's explosive birth, stretched and cooled over billions of years as the cosmos expanded. Its uniformity and slight variations tell us a compelling story about the universe's infancy. One of the most fascinating aspects of the CMB is its astonishing uniformity. Across vast expanses of space, the temperature of this radiation is incredibly consistent, about 2.7 Kelvin or minus 270.45 degrees Celsius, with minuscule fluctuations. These minute temperature variations are crucial for cosmologists because they represent the seeds from which galaxies, stars, and eventually planets formed. Essentially, these fluctuations in density and temperature underpin the large-scale structure of the universe we observe today. The CMB also serves as a profound probe into the composition of the early universe. By studying its light, scientists can infer the universe's makeup at that time, revealing a cosmos filled predominantly with hydrogen and helium, the simplest and most abundant elements. This elemental composition supports theories of nucleosynthesis, predicting how the first elements formed in the universe's nascent moments. The polarization of the CMB light, akin to the way certain sunglasses can block out glare by aligning light waves, offers additional clues about the early universe. Polarization patterns in the CMB can be traced back to gravitational waves rippling through the infant universe, providing indirect evidence for inflation. Inflation is a theory suggesting that the universe underwent an exponential expansion in its first fractions of a second, smoothing out and shaping the universe's structure. Another intriguing insight from the CMB is the glimpse it offers into the nature of dark matter and dark energy, mysterious components that constitute most of the universe's mass energy content. The way CMB radiation is scattered and its interaction with matter over cosmic timescales helps cosmologists map out the influence of dark matter in clumping matter together and the role of dark energy in accelerating the universe's expansion. In the wake of the Big Bang, the universe was a formless expanse of energy, primed to evolve into the structured cosmos we observe today. This transition from chaos to order was governed by the emergence and shaping of the laws of physics, fundamental principles that dictate the behavior of the universe. Initially, in the universe's first moments, temperatures were unimaginably high, and the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. As the universe cooled, these forces began to separate, a process pivotal to the formation of the cosmos as we know it. The first to split was the strong nuclear force, responsible for holding the nuclei of atoms together. This separation set the stage for the formation of the first subatomic particles, including quarks and electrons, mere fractions of a second after the Big Bang. As the universe continued to expand and cool, quarks coalesced to form protons and neutrons, the building blocks of atoms. This period, known as the quark epoch, was crucial for determining the amount and types of matter that would dominate the universe. Following this, the universe entered the electroweak epoch, where the electromagnetic and weak nuclear forces distinguished themselves. This differentiation was vital for the creation of various types of particles and antiparticles, and for the processes that led to the predominance of matter over antimatter in the universe. Without this asymmetry, matter and antimatter would have annihilated each other, leaving the universe devoid of the galaxies, stars, and planets we see today. As the universe aged, it cooled sufficiently for the first atoms to form, a phase known as recombination, occurring around 380,000 years after the Big Bang. This was a pivotal moment, as it allowed photons, particles of light, to travel freely for the first time, creating the cosmic microwave background radiation, a snapshot of the universe at that time. The laws of physics, particularly electromagnetism, played a crucial role in this process, dictating how electrons and nuclei combine to form neutral atoms. Gravity, the weakest but most far-reaching force, began to sculpt the large-scale structure of the universe during this period. Regions slightly denser than their surroundings began to collapse under their own gravity, forming the first stars and galaxies. This gravitational clustering is a process that continues to shape the cosmos, driving the formation of galaxy clusters and superclusters. Over billions of years, the interplay of these forces under the laws of physics facilitated the evolution of the universe from a hot, dense state to the vast and varied cosmos we observe today. Elements formed in the hearts of stars were scattered into space by supernovae, seeding the cosmos with the building blocks for new stars, planets, and eventually life. The laws of physics, emerging in the aftermath of the Big Bang, not only dictated the creation and behavior of the universe's fundamental particles, but also guided the evolution of the cosmos from simplicity to complexity. As we delve deeper into the mysteries of the cosmos, the process of galaxy formation and evolution stands as a cornerstone of modern astrophysics, offering a window into the dynamic ballet of matter under the influence of gravity in an expanding universe. This narrative unfolds over billions of years, tracing back to the subtle fluctuations in the density of matter shortly after the Big Bang, which we've seen imprinted in the cosmic microwave background radiation. The story begins in the primordial soup of the early universe, a nearly uniform field peppered with slight overdensities. These overdensities, though minuscule, were the seeds of all future structures in the universe. Under the relentless pull of gravity, regions of higher density began to attract more matter, growing increasingly larger and denser. This gravitational accretion was a first step in the long journey of galaxy formation. As these regions pulled in more gas and dark matter, a mysterious form of matter that does not emit, absorb, or reflect light, but exerts gravitational effects on visible matter, they began to collapse under their own gravity. This collapse led to the formation of dark matter halos, invisible scaffolds around which visible matter could clump together. Within these dark matter halos, gas clouds continued to collapse, heating up as they densified, until the conditions became ripe for the birth of stars. This marked the emergence of the first galaxies, simple and small compared to the vast spiral and elliptical galaxies we observe today. Over time, these early galaxies began to evolve and interact. Some merged, pooling their stars and gas to form larger galaxies, while others were torn apart by gravitational forces. This era of cosmic evolution was chaotic, marked by frequent collisions that spurred bursts of star formation, known as starbursts, which shaped the galaxy's structures and compositions. Galaxy evolution is also a tale of internal change. Stars within galaxies live their lives on timescales ranging from millions to billions of years, depending on their masses. Massive stars burn through their nuclear fuel rapidly, ending their lives in supernova explosions that seed the galaxy with heavier elements. These elements, in turn, become the building blocks of new stars and planets, enriching the galaxy and influencing future generations of stars. Meanwhile, the supermassive black holes that lurk at the centers of most, if not all, large galaxies also play a crucial role in shaping their host galaxies. As these black holes accrete matter, they can emit vast amounts of energy, influencing star formation across the galaxy. Through these processes, galaxies grow and evolve, their shapes and sizes reflecting their histories of formation, interaction, and internal processes. Spiral galaxies, with their rotating disks and spiral arms, elliptical galaxies, ranging from nearly spherical to elongated ovals, and irregular galaxies, with no distinct shape, all tell stories of their origins and the dynamic universe in which they reside. As we explore the cosmos, supermassive black holes emerge as cosmic architects, exerting a profound influence on the galaxies they inhabit. Lurking at the heart of nearly every large galaxy, these colossal entities, with masses ranging from millions to billions of times that of our Sun, play a key role in shaping the evolution and characteristics of galaxies. Supermassive black holes are not just cosmic oddities. They are central players in the galactic narrative. Their gravitational pull can dictate the motion of stars and gas clouds within a galaxy, influencing its overall structure and dynamics. But their influence extends beyond mere gravitational sway. As material spirals into a supermassive black hole, it heats up and emits intense radiation across the electromagnetic spectrum, from radio waves to X-rays. This radiation can have far-reaching effects on the galaxy's environment. One of the most dramatic impacts of supermassive black holes is their role in regulating star formation within galaxies. The process, known as feedback, occurs when the energy released by the black hole as it accretes matter heats up and disperses the surrounding gas clouds that would otherwise collapse to form new stars. This feedback mechanism can quench star formation, effectively halting the growth of the galaxy. It's a delicate balance. Too much activity from the black hole can blow away the galaxy's gas, starving of the material needed for future stars, while too little can lead to unchecked star formation, dramatically altering the galaxy's character. The interaction between supermassive black holes and their host galaxies is a dynamic dance. The growth of these black holes is closely linked to the evolution of their galaxies. Observations suggest a correlation between the mass of a supermassive black hole and the properties of its host galaxy's bulge, the dense group of stars at the galaxy's center. This relationship implies that the growth of black holes and galaxies is interconnected, possibly through cycles of gas accretion and star formation regulated by the black hole's feedback. In addition to their role in regulating star formation, supermassive black holes can also drive the formation of galactic structures. For example, jets of material ejected at near-light speeds from the poles of actively accreting black holes can carve out vast cavities in the intergalactic medium, influencing the distribution of gas and the formation of galaxy clusters. Supermassive black holes also contribute to the cosmic ecosystem through their dramatic end-of-life events. When galaxies merge, a common occurrence in the cosmic history, their central black holes can eventually collide and merge, releasing vast amounts of energy in the form of gravitational waves. These ripples in the fabric of space-time can provide insights into the fundamental laws of physics and the violent processes at the heart of galaxy evolution. Let us talk a bit about stars. The life cycle of a star is a story of transformation, a journey that not only shapes the destiny of the star itself, but also plays a pivotal role in the creation of elements, the building blocks of the universe. This cycle begins in the cold, dark clouds of interstellar gas and dust, where the seeds of stars lie waiting for the spark of creation. The first stage in the life cycle of a star is its birth, which occurs in nebulae, immense clouds of gas and dust. Within these nebulae, regions of higher density, aided by the gravitational pull of existing matter, begin to collapse under their own gravity. As the gas clumps together, it heats up, and when the core of this collapsing cloud reaches a sufficient density and temperature, nuclear fusion ignites. This fusion process marks the birth of a new star, converting hydrogen into helium and releasing energy in the form of light and heat. This is how a star enters the main sequence phase of its life, a period of stability where it spends most of its existence, balancing the outward pressure of nuclear fusion with the inward pull of gravity. The next stages in a star's life depend on its mass. Medium-sized stars, like our Sun, will swell into red giants as they exhaust their hydrogen fuel and begin to fuse helium into heavier elements like carbon and oxygen. Eventually, these stars shed their outer layers into space, creating beautiful objects known as planetary nebulae. What remains is a core, which collapses into a white dwarf, a dense, hot remnant that slowly cools and fades over billions of years. For more massive stars, the journey is even more dramatic. After burning through their initial hydrogen, they progress to fusing heavier elements, ultimately leading to iron in their cores. Fusion stops at iron because fusing iron consumes more energy than it releases, leading to a catastrophic collapse of the star's core. This collapse triggers a supernova explosion, an event so powerful it can briefly outshine an entire galaxy. Supernovae are crucial for element formation, as they produce and scatter many of the heavier elements beyond iron throughout the cosmos. The remnants of these explosions can form either a neutron star, an incredibly dense object composed mostly of neutrons, or if the star was sufficiently massive, a black hole, a point in space where gravity is so strong that not even light can escape. Stars, through their life cycles, are the universe's forges, creating and distributing the elements that make up worlds and life itself. Every atom of carbon, oxygen, and iron in our bodies was formed in the heart of a star or in the fiery blast of a supernova, linking us intimately to the cosmos. Supernovae, neutron stars, and black holes represent some of the most dramatic and significant phenomena, each playing a unique role in the universe's evolution and in our understanding of physics. These celestial events and objects are not only fascinating in their own right, but also crucial for the synthesis of elements and the structure of the cosmos. Supernovae are the spectacularly explosive deaths of stars, events so bright they can momentarily outshine entire galaxies. They occur in two main scenarios, either at the end of a massive star's life, when its core collapses under the force of its own gravity, or through the accumulation of material by a white dwarf from a companion star, leading it to exceed a critical mass and undergo a thermonuclear explosion. Supernovae play a critical role in the cosmos by dispersing elements heavier than iron into space. These elements, forged in the heart of stars or during the supernova explosion itself, are essential for the creation of planets and life. The energy released by supernovae also influences the structure of the surrounding interstellar medium, triggering star formation in some regions while dispersing gas and dust in others. Neutron stars are one of the possible remnants of supernovae explosions, formed when the core of a massive star collapses to such an extent that protons and electrons combine to form neutrons. These objects are incredibly dense, with a mass comparable to that of the Sun, but packed into a sphere only about 20 kilometers in diameter. Neutron stars possess intense gravitational and magnetic fields, with some emitting regular pulses of radiation as pulsars. These pulsars serve as cosmic lighthouses and have been used by astronomers to probe the universe's properties, including testing theories of gravity and measuring cosmic distances. Black holes, the most mysterious of these cosmic phenomena, form when the core of a supermassive star collapses under its gravity, creating a point in space where the gravitational pull is so strong that not even light can escape. Their existence was predicted by Einstein's theory of general relativity, and they have been the subject of intense study ever since. Black holes play a significant role in the dynamics of galaxies. Supermassive black holes at the centers of galaxies regulate star formation and galaxy evolution through their gravitational influence and the energetic processes associated with the accretion of matter. The significance of supernovae, neutron stars, and black holes extends beyond their role in cosmic element synthesis and structure formation. They are natural laboratories for extreme physics, allowing scientists to study conditions of gravity, density, and energy that are unattainable on Earth. The observation and modeling of these phenomena have led to profound insights into the nature of matter, space, and time, challenging and enriching our understanding of the universe. Planetary systems and exoplanets. The formation of planetary systems around stars is a captivating chapter in the cosmic narrative, revealing how the swirling clouds of gas and dust coalesce into the diverse worlds that orbit our universe's countless stars. This process, while complex, begins with the collapse of a molecular cloud, much like the birth of stars themselves. Within these vast clouds, pockets of increased density, perhaps nudged by the shockwave from a nearby supernova, begin to collapse under their own gravity, forming a rotating disk of gas and dust around a new central star. This star, fueled by nuclear fusion, lights up its corner of the cosmos, while the material in the surrounding disk begins the intricate dance of planet formation. Over time, particles within the disk collide and stick together, forming clumps that grow into planetesimals, the building blocks of planets. Through a process of accretion, these planetesimals continue to collide and merge, growing into protoplanets. The inner part of the disk, where it is hotter, tends to form rocky planets like Earth and Mars. In contrast, the outer regions, where it's cold enough for ice to form, give rise to gas giants and icy worlds. But the journey from a swirling disk of debris to a bustling planetary system is influenced by several factors, not least of which is the central star's properties. Its mass, luminosity, and magnetic activity can significantly impact the formation process and the eventual composition of the planetary system. Additionally, interactions between emerging planets can lead to dynamic changes, with some being ejected from the system or colliding with others to form larger bodies. When considering what makes a planet habitable, the concept of the habitable zone, or the Goldilocks zone, comes to the forefront. This zone is a range of distances from a star where conditions might be just right, not too hot and not too cold, for liquid water to exist on a planet's surface, a crucial factor for life as we know it. However, being in the habitable zone is just one piece of the puzzle. A planet's atmosphere and magnetic field can also play critical roles in maintaining surface conditions conducive to life. An atmosphere can regulate temperature, protect the surface from harmful radiation, and provide essential elements for life, while a magnetic field can shield the planet from stellar winds, preserving its atmosphere over time. The planet's composition, geological activity, and the presence of water in liquid form are essential factors that contribute to its habitability. Geological activity, for instance, can recycle carbon through the planet's mantle and atmosphere, stabilizing the climate over geological timescales. The quest to discover exoplanets, planets beyond our solar system, employs a fascinating array of methods, each unveiling new worlds in the vast expanse of space. This pursuit not only expands our understanding of planetary systems, but also brings us closer to answering the age-old question: are we alone in the universe? One of the most successful techniques for finding exoplanets is the transit method, which detects the slight dimming of a star's light as a planet passes in front of it. This method has been particularly fruitful, thanks to missions like NASA's Kepler Space Telescope, which monitored the brightness of thousands of stars, uncovering a diverse array of exoplanets. Another technique is the radial velocity method, which measures the star's motion towards and away from us, caused by the gravitational tug of an orbiting planet. This method can provide information about the planet's mass and its orbit. Direct imaging, though challenging, involves capturing actual images of exoplanets by blocking out the star's light, allowing astronomers to study the planet's atmosphere. Meanwhile, the gravitational microlensing method relies on the bending of light from a distant star caused by a planet's gravitational field, briefly magnifying the distant star's light in a way that can reveal an orbiting planet. Among the thousands of exoplanets discovered, several stand out for their unique characteristics or potential habitability. For instance, Kepler 22b was one of the first planets found in the habitable zone of its star, raising possibilities of liquid water on its surface. Another intriguing world is TRAPPIST-1e, one of 7 Earth-sized planets orbiting the dwarf star TRAPPIST-1, which has captured imaginations with its potential for water and habitability. Then there's Proxima Centauri b, located in the habitable zone of Proxima Centauri, the closest star to the Sun. Its discovery sparked excitement about the possibility of studying a potentially habitable planet that's relatively nearby in cosmic terms. Meanwhile, HD 209458b, known as OSIRIS, stands out for being the first planet where an atmosphere was detected, offering a glimpse into the composition of exoplanetary atmospheres. Each of these discoveries brings a unique insight into the diversity and complexity of planetary systems across the galaxy. They also underscore the remarkable progress in our ability to detect and study distant worlds, moving us closer to understanding the conditions that might support life elsewhere in the cosmos. Galaxy dynamics. The interactions between dark matter and baryonic matter, the normal matter that makes up stars, planets, and all visible objects, play a crucial role in shaping the structure and dynamics of galaxies, influencing both their shape and rotation curves in significant ways. Dark matter, though invisible and not directly detectable, constitutes about 85% of the universe's total matter content. Its presence is inferred from its gravitational effects on visible matter, light, and the structure of the universe. One of the key insights into dark matter comes from observing galaxy rotation curves, the way the velocity of stars and gas clouds orbiting the galaxy center changes with distance from the center. According to Newtonian mechanics, one would expect the rotational speed of objects orbiting a galaxy's center to decrease with distance from the center, similar to how planets in the solar system orbit the sun. However, observations show that the rotational speeds of stars and galaxies remain constant or even increase slightly with distance from the galactic center, defying these expectations. This discrepancy suggests the presence of a substantial amount of unseen mass attributed to dark matter, exerting gravitational influence. Dark matter forms vast halos that envelop galaxies, extending far beyond the visible edge of the galaxy. The gravitational pull of this dark matter halo is what keeps stars moving at higher velocities than would be expected based solely on the visible mass. This not only explains the flat rotation curves of galaxies, but also plays a critical role in their formation and evolution. During the early stages of the universe, dark matter clumps formed the gravitational scaffolding around which baryonic matter coalesced to form stars, galaxies, and larger structures. The distribution and density of dark matter in these halos influenced the shape and type of galaxies that formed. For instance, dense, compact halos might lead to the formation of elliptical galaxies, while more extended halos with specific angular momentum distributions can give rise to spiral galaxies. The interactions between dark matter and baryonic matter are essential for understanding the large-scale structure of the universe. Dark matter's gravitational effects enhance the clumping of matter in certain regions, leading to the web-like structure of the cosmos, with galaxies and clusters of galaxies linked by filaments of dark matter and separated by vast voids. Discoveries about the intergalactic medium, or IGM, have significantly reshaped our understanding of galaxy formation, highlighting the dynamic and interconnected nature of the universe. The IGM, which consists of diffuse gas and plasma that fills the vast spaces between galaxies, plays a critical role in the cosmic web's structure and evolution, acting as both a reservoir for galaxy formation and a record of the processes that shape the universe. One key discovery is the detection of the cosmic web, a vast network of filamentary structures composed of dark matter and gas that stretches across the universe, linking galaxies and galaxy clusters. Observations, particularly through the absorption lines in the spectra of distant quasars, bright, active galaxies far away, have revealed the presence of hydrogen and other elements in the IGM. These absorption lines, known as the Lyman Alpha Forest, have provided valuable insights into the distribution, temperature, and composition of the IGM, confirming the existence of the cosmic web and its role in galaxy formation. The realization that the IGM is not only a repository of matter, but also a dynamic participant in galaxy evolution has been transformative. Gas from the IGM falls into the gravitational wells created by dark matter, cooling and condensing to form stars and galaxies. This process, known as accretion, is fundamental to galaxy formation and growth. Furthermore, feedback mechanisms from star formation and active galactic nuclei, where energy is injected back into the IGM, regulate the flow of gas into and out of galaxies, influencing their ability to form stars. Another groundbreaking discovery has been the detection of the missing baryons. Early observations of galaxies and galaxy clusters accounted for only a fraction of the ordinary matter predicted by the Big Bang Theory. Studies of the IGM have uncovered these missing baryons in the form of warm-hot intergalactic medium, or WIM, a tenuous, partially ionized gas that permeates the filaments of the cosmic web. The WIM had been difficult to detect due to its diffuse nature and the high temperatures at which it emits and absorbs radiation, but recent observations, using X-ray and ultraviolet telescopes, have begun to reveal its properties and distribution. Stellar evolution and end states. The mass of a star is the principal determinant of its life cycle, dictating not only how the star lives but also how it dies. This mass influences the star's core pressure and temperature, determining the nuclear fusion reactions that can occur and thus the star's luminosity, temperature, and lifespan. Depending on its initial mass, a star may end its life as a white dwarf, neutron star, or black hole, each marking a different evolutionary path in the cosmos. Stars with masses up to about 8 times that of the Sun follow a similar evolutionary path. They spend the majority of their lives fusing hydrogen into helium in their cores, a phase known as the main sequence. Once the hydrogen fuel is exhausted, these stars expand into red giants, where the core contracts and heats up, enabling the fusion of helium into carbon and oxygen in a shell around the core. For stars like the Sun, this is where nuclear fusion essentially ends. When the nuclear fuel is depleted, the outer layers of the star are ejected, creating a planetary nebula, while the core remains as a white dwarf, a hot, dense remnant, roughly the size of Earth, but with a mass close to the Sun's. White dwarfs gradually cool and fade over billions of years. Stars with masses significantly greater than the Sun undergo more complex and energetic lives. After exhausting their hydrogen, these stars become supergiants and can fuse heavier elements in their cores, sequentially burning through helium, carbon, oxygen, and so on, up to iron. Iron fusion, however, consumes energy rather than releases it, leading to a rapid core collapse. Once a significant amount of iron has accumulated, this collapse triggers a supernova explosion, one of the universe's most spectacular events. The star's outer layers are blown away, while the core collapses into an extremely dense object. If the core's mass is about 1.4 to 3 times that of the Sun, the Chandrasekhar limit, it becomes a neutron star, an object so dense that protons and electrons combine to form neutrons. A sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. For cores with masses exceeding roughly 3 solar masses, The gravitational collapse results in a black hole, a point in space where gravity is so strong that not even light can escape. The Schwarzschild radius, or event horizon, marks the boundary beyond which nothing can return. The mass of a star, therefore, sets the stage for its entire life and ultimate fate, from tranquil existences marked by gentle winds of ejected material to violent ends that outshine galaxies. These end states, white dwarfs, neutron stars, and black holes, contribute to the cosmic cycle of matter, seeding the universe with the heavy elements forged in their crucibles, elements that will become part of future stars, planets, and possibly life forms, continuing the grand cycle of cosmic evolution. Dark energy, a mysterious force that is accelerating the expansion of the universe, constitutes about 68% of the universe's total energy. Its discovery in the late 1990s, through observations of distant supernovae, has profoundly shifted our understanding of the cosmos, presenting new questions about the universe's fate and the laws that govern it. The latest theories and experiments aimed at understanding dark energy are diverse, ranging from modifications of Einstein's theory of general relativity to innovative observational campaigns. One leading theoretical approach is the concept of quintessence, a dynamic field that changes over time and space, unlike the cosmological constant, which Einstein originally introduced to his equations of general relativity to allow for a static universe and later abandoned. Quintessence models suggest that the strength of dark energy could vary, providing a possible explanation for why the expansion of the universe is accelerating now, after billions of years of deceleration following the Big Bang. Another area of exploration involves theories of modified gravity, which propose that the observed acceleration could be due to new aspects of gravity not accounted for in general relativity, especially over large scales. These theories challenge our fundamental understanding of gravity and require rigorous testing through observations. On the experimental front, several ambitious projects are underway to probe the nature of dark energy and its effects on the cosmos. The Dark Energy Survey, DS, using a powerful digital camera mounted on a telescope in Chile, has mapped millions of galaxies to study the structure of the universe over vast scales and time periods. By analyzing how clusters of galaxies have grown over time under the influence of dark energy, scientists hope to shed light on its properties. Similarly, the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, promises to provide unprecedented insights into dark energy. By surveying the sky in detail over 10 years, LSST aims to uncover the nature of dark energy by observing billions of galaxies and tracking how the universe's expansion has evolved. Another pioneering effort is the Euclid mission, a space telescope developed by the European Space Agency, scheduled for launch in the near future. Euclid is designed to map the geometry of the dark universe by measuring the distribution of galaxies and the bending of light, gravitational lensing, caused by dark matter and dark energy, offering clues about the underlying physics driving the universe's expansion. Gravitational lensing, a phenomenon predicted by Albert Einstein's general theory of relativity, has become an invaluable tool in the study of dark matter distribution across the universe. This phenomenon occurs when the gravitational field of a massive object, such as a galaxy or cluster of galaxies, warps the fabric of space-time around it, bending the path of light from a more distant object. This effect can magnify, distort, and even produce multiple images of the background object, depending on the alignment between the observer, the foreground mass, and the background light source. Gravitational lensing observations are particularly powerful for studying dark matter because dark matter does not emit, absorb, or reflect light, making it invisible to traditional telescopic observations. However, dark matter does exert gravitational forces, influencing the motion of stars within galaxies, the gas in galaxy clusters, and the path of light through the universe. By analyzing the light from distant galaxies and quasars that has been bent by intervening dark matter, astronomers can map the distribution and concentration of dark matter. Even though it cannot be seen directly, there are two primary types of gravitational lensing: strong and weak. Strong lensing occurs when the foreground object is massive enough, and the alignment is such that it creates highly distorted or multiple images of the background object. Strong lensing can create striking phenomena, such as Einstein rings, where a perfectly aligned lensing object produces a circular image of the light source. By studying these rings and multiple images, astronomers can directly map the mass distribution of the lensing object, revealing the presence and structure of dark matter. Weak lensing, though subtler, is more common and occurs when the distortion of background objects is slight. This form of lensing affects the shapes of numerous distant galaxies slightly, causing a coherent distortion pattern that can be detected statistically over large areas of the sky. By measuring the shape distortions of millions of galaxies, astronomers can create detailed maps of the dark matter distribution on large scales, revealing the cosmic web of dark matter that underlies the visible universe. Gravitational lensing has provided some of the most direct evidence for dark matter, confirming its existence and providing insights into its properties. For example, observations of colliding galaxy clusters, such as the Bullet Cluster, have used gravitational lensing to separately map the distribution of dark matter and ordinary matter. These observations have shown that dark matter interacts only through gravity, bypassing other forces that affect normal matter, a key piece of evidence supporting the dark matter hypothesis. Interstellar phenomena. The discovery of Oumuamua in October 2017 marked a milestone in astronomy and our understanding of the cosmos. As the first confirmed interstellar object to pass through our solar system, Oumuamua's appearance challenged our preconceptions and opened up new avenues for research into the composition, dynamics, and origins of objects from beyond our solar system. Oumuamua, which means scout or messenger in Hawaiian, was detected by the Pan-STARRS-1 telescope in Hawaii as it made its closest approach to the Sun. Its highly elongated shape, unusual for asteroids or comets within our solar system, and its unexpected acceleration as it passed through the solar system, sparked intense interest and speculation among scientists. The significance of Oumuamua's discovery lies in several key areas. Interstellar visitors. Oumuamua confirmed that objects from other star systems can and do enter our solar system, providing direct evidence of material exchange between stars. This has implications for our understanding of planetary system formation and evolution, suggesting that the building blocks of planets and potentially the precursors of life could be exchanged between distant star systems. Composition and origins. Initial observations suggested Oumuamua was an asteroid, but its lack of a cometary tail as it approached the Sun puzzled astronomers. Later studies proposed it might be a new type of object, possibly a fragment from a disintegrated comet or even a piece of interstellar debris. Understanding Oumuamua's composition and origins could provide insights into the processes at work in other planetary systems and the diversity of objects formed in these distant environments. Oumuamua exhibited non-gravitational acceleration, changes in its speed and trajectory that couldn't be explained solely by the Sun's gravity. This led to various hypotheses, including outgassing, the release of gas from its surface, which is common in comets but had not been directly observed in Oumuamua due to the lack of a visible coma or tail. This behavior has prompted discussions about the mechanisms that could cause such acceleration in interstellar objects. The discovery of 2I/Borisov in August 2019 by amateur astronomer Gennady Borisov marks another monumental step in our exploration of the cosmos, being the second interstellar object detected passing through our solar system and the first confirmed interstellar comet. Unlike Oumuamua, whose origins and classification sparked widespread debate among scientists, Borisov was readily identified as a comet due to its distinct cometary features, including a glowing coma and a tail, which are characteristic of comets as they approach the Sun and their icy bodies begin to sublimate. What fascinating mysteries do you believe exist in the universe? From the enigmatic dark matter and dark energy that seem to govern the cosmic structure and expansion, to the tantalizing prospect of parallel universes and the mysteries of black holes, where the known laws of physics converge and diverge in unpredictable ways. Our quest for understanding is far from over, Each discovery peels back a layer, revealing not just answers, but a multitude of new questions, each more intriguing than the last. Let us know your thoughts and ideas in the comments below. Thanks for watching, and subscribe to our channel for more videos like this.